Dear students, welcome back to the online sessions on AEC. In the last chapter, we have completed Class B power amplifier operation. So usually Class B comes with a designation as push-pull type of the amplifier. We simply call it as a Class B push-pull type of the power amplifier. Okay, there are two types of Class B power amplifiers. One is going to be push-pull amplifier and a complementary symmetry power amplifier circuit. So we discussed in the last session, that is the Class B push-pull power amplifier basic operation, right? In today's session, what we do is we go with the expression for efficiency in the Class B push-pull power amplifier and also the drawbacks of the Class B push-pull power amplifier. And then we simply extend our discussion on how to overcome the drawback of the Class B push-pull power amplifier. Okay, so let us go with the derivative part for the efficiency of Class B push-pull power amplifier circuit. So we discussed operation of this Class B push-pull type of the power amplifier. Now, whenever a question is asked on Class B push-pull power amplifier, complementary symmetry push-pull power amplifier, Class AB type of the power amplifier, and in fact Class D type of the power amplifier, all these amplifiers looks alike. That is Class B push-pull, complementary symmetry, Class AB and Class D power amplifiers looks almost alike with a minute differences in the circuit. So you should be careful while drawing these diagrams. That means you should be very much careful while drawing the circuit diagrams of Class B push-pull, Class B complementary symmetry, Class AB power amplifier and Class D power amplifier circuits, because all these circuits looks alike with a minute changes in the circuit. So you should be very much careful while you draw these circuit diagrams. Class A power amplifier with and without transformer coupling is very easy to draw, but other circuits is little bit confusing, so that you should be very much careful, okay, in drawing these circuit diagrams. Okay, so this is a Class B push-pull power amplifier. Here in this we have used two transformers. One is at the primary, another one is at the secondary transistor. At primary, in order to couple the signal to the input signal, we are using an input transformer, and in order to couple the output of the amplifier to the loudspeaker, we are using the output transformer. Okay, because the input resistance of the loudspeaker is going to be very, very small, and the secondary turns, if you're going to use a step down transformer, the secondary turns resistance is also going to be very much less. Thereby we achieve the impedance matching here. Okay, so just for this particular reason we are going to use the transformer coupling. Okay, so if you use transformer coupling, what advantage we get? We get impedance matching. Because of impedance matching, we get a maximum power transfer into the load. That is known as the loudspeaker in general. Therefore, we have used the transformer at the output as well. Okay. Now, if you see these transistors in the case of Class B push-pull type of the power amplifier, the two transistors that you're going to use are going to be of NPN type, NPN type. This is the important point. See, T1 transistor is NPN type, T2 transistor is NPN type. How can you say? The arrows which are shown in this transistor symbol are simply coming out. See here, T1 transistor arrow is coming out. T2 transistor arrow is also coming out of the node of the transistor. So if the arrow is coming out, it is known as NPN type of the transistor. So that means we will be using the two NPN type of the transistors, and these two transistors are constructed based on the common emitter configurations. So these two are something like common emitter type of the configuration. That means emitter is simply connected to the ground. That means it comes under the common emitter configuration circuit. Now, this is what the point which we have to remember compulsorily here. So because of common emitter configuration, what is the output we get? This T1 transistor is going to transmit positive part of the input signal. T2 is going to transmit the negative part of the input signal. So after the T1 transistor transmits positive part, the output signal will be getting as an inverted signal. because of CE operation. CE amplifier is always going to produce an inverted output with respect to the input. That means the phase of the input signal, the phase of the output signal and input signal are going to be 180 degrees out of phase. Okay, that means the transistor amplifier is going to invert the input signal by 180 degrees. That is what the inversion we are seeing here. So you have to draw all these waveforms in the exam so that you can get full marks. Then T2 transistor is going to operate with a negative cycle, negative half cycle. So this negative half cycle is transmitted by the amplifier, and this negative half cycle is simply converted into the positive half cycle. These two cycles are going to get added at the secondary side, and at the output we normally going to get a complete waveform, which is a combination of positive as well as negative. Okay, so this is how we normally going to got the output waveform of the class B push-pull type of the power amplifier circuit. Now, due to the operation of the class B push-pull power amplifier, the output of a single amplifier is normally drawn over here, because we are interested in getting the output waveform of a single transistor especially. So therefore, the output of a single transistor we have drawn, where we will be getting a half wave of the input signal. See here, we have got half wave, then there is a gap, then half wave. For the current also, there is a half wave, there is a gap, then there is going to be a half wave, right? That means this gap, in this gap, what happens? Another transistor will be in the on condition. That means when one transistor is in the on condition, other has to be in the off condition. When other transistor is in the on condition, the first transistor should be in the off condition. That means both cannot be in the off condition simultaneously. That is what the major requirement or important requirement in the case of the push-pull type of the power amplifier circuits. So both the transistors should not be in the off condition under any condition or under any time interval. Then only we are normally going to achieve the appropriate output response. Okay. Now this is what we have got. Now, what is the maximum voltage swing we can get here? As a voltage, it can be stretched up to 0. Now, where is the Q point now? The operating point is simply residing on the x-axis. Residing on the x-axis means what? Whatever the signal coming above the Q point is considered as a signal under consideration. That means if you adjust your Q point at a VCC, that is VCE max is equal to VCC, you can get a maximum voltage swing at the output of one of the transistor circuit. That is what the advantage here. See, in comparison to class A, we have to understand the operation of class B type of the power amplifier circuit. Okay. That means in the case of the class B power amplifier, the Q point is normally residing on the x-axis or on the voltage axis. Whereas in the case of class A power amplifier, Q point is adjusted at the center of the active region, so that you are going to have a positive peak as well as negative peak, or positive swing and negative swing of the output signal. Whereas in the case of class B power amplifier, you will be having only one swing, either positive or negative, but not both at the same time for a single transistor circuit. Okay, for a single transistor is going to process only one cycle. That means what is the firing angle now? The firing angle is normally equal to 180 degrees. That means the class of a power amplifier is simply decided by the operating point Q. If the operating point Q is adjusted such that only 180 degrees of the input signal is going to get transmitted to the output side, output circuit, it comes under the class B type of the power amplifier. If the Q point is adjusted such that the complete cycle of the input signal is transmitted, is called class A type of the power amplifier. That means by seeing these waveforms, where we can see that the operating point is only above the Q point. Now below Q point, nothing is there. It is simply cut off. No signal we get. Okay, because Q point has to be, if it is at the center, we can draw a DC load line like this, and we normally going to draw the AC signal like this on this. But the Q point is adjusted here, means what? We can have only voltage above the Q point to 0. That means the stretching is more here. See the stretching here? The voltage swing has been stretched more. One single peak has been stretched more. Okay, so this is the advantage. That means we can get a maximum output voltage because of the class B type of the power amplifier circuit. Okay, well, so this is what the output response which we have seen with respect to the output characteristics. Okay, now we should go into the derivation for the power efficiency of the class B push-pull power amplifier circuit. Now, if you see the output response, the output of the class B amplifier is looking like a half-wave rectified output. If you see this output response, is it not looking like half-wave output? Yes, it is going to be a half-wave rectified output. There is a signal here in this time period. There is no signal here. There is a signal here. Then there won't be a signal. Then there is going to be a signal. That means this response is similar to the half-wave rectifier output. Therefore, we directly use the formula that we have used in the half-wave rectifier circuit. That means the average DC signal can be written as equal to IC max by pi. Okay, that means IDC is equal to the maximum current that can flow through the collector by pi is nothing but IDC. So IDC is equal to I by pi or IC by pi, which we have got already in the case of the rectifier circuits. Now, since we have two transistors, therefore we can write this overall current going to be equal to 2 times IDC. Okay. Now, what about the power? Input power. Input power is nothing but the DC power. So DC power is equal to, what is the formula we can write? IDC into VCC. Now IDC is going to become 2 times IDC. Therefore, I can write 2 times IDC into VCC. What is IDC? It is simply IC max by pi I can write. So this factor 2 is just because of 2 transistors. Okay. Now we have to compute the RMS value. In order to get the voltage in terms of AC, we have to consider RMS values. That means whenever AC voltage signal need to be calculated, you have to first of all find out the RMS value. Therefore, RMS value of the output collector current I can write as equal to IC max by √2. Rated value is nothing but RMS value. RMS value is nothing but is equal to, what is the formula? It is something like Im by √2. So here Im is nothing but maximum collector current, IC max by √2. Similarly, the RMS value, maximum RMS value that we can get at the output is going to be what? VCC by √2. Why VCC? Just now we have seen here earlier in the output characteristics of a class B push-pull type of the power amplifier. See, this is VCC. VCEQ is adjusted equal to VCC. That means what? What is the maximum value we can get? VCC. Therefore, I can write the maximum value going to be as simply VCC by √2. That means VCC is nothing but equal to VM for us. So RMS value of the output voltage is equal to maximum voltage that we can get at the output of the transistor by √2. Under ideal conditions of maximum power, what we can write? Output power, AC output power is equal to IC max by √2. So it is nothing but equal to AC output power is equal to IRMS into VRMS. IRMS is equal to IC max by √2. VRMS is equal to VCC by √2. √2 into √2 is equal to 2. So therefore, I can write IC max into VCC by 2. Now, what about the efficiency formula? Efficiency formula is nothing but equal to output power by input power. Now, in the case of the power amplifiers, output power will be in terms of AC. Input power will be in terms of DC. Means what? The power amplifiers are going to convert AC power into DC power. Sorry, it's a reverse of this. The power amplifiers are going to convert DC power into the AC power. So the input to the power amplifier is equal to what now in terms of power? It is the DC power. What is the output power we'll interested to get? AC power. So output is nothing but AC. Input is nothing but DC. Exactly reverse is going to be true for rectifiers. What about rectifier? Rectifier should produce output as DC. Therefore, in the case of rectifiers, what is the expression for efficiency? It is output power by input power is efficiency. That means DC output power by AC input power is the formula for efficiency in rectifiers. Whereas coming to power amplifiers, it is reverse. That is AC output power by DC input power. Okay. Now what is AC output power? It is IC max into VCC by 2 into what is DC input power? DC input power we have simply computed as something like this. DC input power is what now? It is nothing but this now. 2 into IC max by pi into VCC is the DC input power. Now, what I can write here? Multiply by. It is, that means I can write this as pi by 2 into IC max into VCC. So when you solve this, IC max will get cancelled, VCC will get cancelled. I get pi by 4. To get a percentage, we multiply it by 100. So thereby I'll be getting this as 78.5%, which is reasonably a good efficiency value. So therefore we can say that class B power amplifier is going to give us a very good efficiency. That means the efficiency of class B push-pull power amplifier is more than the efficiency of a class A transformer coupled amplifier. So the efficiency of class A transformer coupled amplifier is maximum 50%. The efficiency of class B push-pull power amplifier we got here as 78.5%, which is definitely more than 50%, and hence the class B push-pull power amplifier improves the efficiency than the class A type of the amplifier. Okay. So we can connect class A in push-pull configuration also, that we'll see at the end. But for the time being, so class A power amplifier is going to produce maximum efficiency as 50%, right? So this is what regarding the class B type of the amplifier push-pull configuration. Now another example, we have another combination. In the case of the power amplifier, class B power amplifier is going to be complementary symmetry power amplifier. So I can call this as complementary symmetry push-pull class B amplifier, class B power amplifier. We need not say the term as power amplifier. If you say class B, class A, class B, class C, all of them are known as power amplifiers only. So we need not explicitly say it as a power amplifier. They are understood it to be like a power amplifiers. Okay. So complementary means what? We know complementary. In the case of digital circuits, if the signal is complemented, if 0 is complemented, we get 1. If 1 is complemented, we get 0. Complementary is something like inverted version. So in the case of transistors, we have two types of transistors known as NPN and PNP type of the transistors. Now these two are going to have inverted operations in comparison to the other. How can we say that? The arrow mark. If arrow is coming out of the node, it is called NPN transistor. If the arrow is going into the node, it is known as PNP type of the transistor. Okay. This is what symbolical difference. Next difference is going to be what now? The NPN transistor is normal. The output circuit of the NPN transistor is going to get reverse biased by applying a positive VCC. Reverse bias voltage is applied with positive VCC. Exactly reverse is going to be true here. In the case of PNP transistor, so the output circuit is reverse biased by negative VCC. That means you have to apply two supply voltages, plus VCC and minus VCC, because we are using the complementary symmetry amplifier circuits. That is the thing we are going to have. Now, what is the problem here is, in the case of complementary symmetry, you should choose the two transistors such as NPN and PNP with the same cut-in voltage. That is what the major problem here. That means choosing the same cut-in voltage is a big challenging task in the case of the complementary symmetry push-pull class B type of the power amplifier circuit. Okay. Now, these two circuits, the bases of these two are simply connected to the same point, and then the transformer is connected between the two supplies, okay, and to a common point to the ground. Okay, so this is the basic circuit diagram which we can simply going to draw to explain about the complementary symmetry type of the push-pull power amplifier circuit. Now, when Q1 will be in the on condition, Q1 will turn into on condition when the input is going positive. Q2 will turn into on condition. This is what called Pnp transistor when the input is going negative. When the input is going negative, Pnp will turn into on condition. When input is going positive, T1 will be turning into on condition. That means input is going to have positive cycle as well as negative cycle. So when the positive cycle comes over here, T1 transistor turns into on condition because it is NPN configuration, because it is NPN type of transistor. When the input is negative half cycle, then NPN, that is T1 transistor, will be in the off condition. T2 will turn into on condition. Thereby what happens? Two half cycles will be simply transmitted to the load, which is connected to the output side of the two transistors. Okay. So this is what the basic circuits which we can just simply going to have in the case of the complementary symmetry push-pull type of the power amplifiers. Now there is a performance bottleneck here in the case of the class B type of the push-pull power amplifiers. That is known as the crossover distortion, which is known as the major drawback of the class B type of the push-pull power amplifier. So the class B push-pull power amplifier, both symmetry, both complementary symmetry as well as push-pull type of the power amplifier, both of them are going to suffer with the crossover distortion. In either cases, in the complementary symmetry push-pull or push-pull type of class AB power amplifier, why the name given as push-pull? One transistor will be pulled up, push it to on condition. At the same time, other transistor will be pulled down into off condition. So that is why we simply name them as push-pull type of the power amplifiers. Okay. So this is what the circuit operation is going to be quite similar. Only thing is the advantage here we're going to get is at the input side of the class B complementary symmetry, there is no transformer. That means the weight of the circuit is simply reduced because at the input there is no transformer coupling. If transformer is there, the weight of the circuit is normally going to increase. If transformer is not there, weight is simply going to reduce drastically. Okay. That is the advantage. Now, what are the advantages of this complementary symmetry? There is no need of center tapped input transformer. That means we don't require the center tapped input transformer. In the case of the complementary symmetry push-pull power amplifier, that means input transformer is not there, means center tapped headache is not there. Then equal and opposite input signal voltage are not required. In the case of complementary symmetry, in the case of the ordinary push-pull amplifier, the peak voltages of the two cycles should be 100% equal. Whereas in the case of complementary symmetry, it need not be. It need not be. Practically what happens, the signal strength cannot be same for positive as well as negative peaks. That is what the practical scenario. So if you really consider such a practical scenario, this is going to be an advantage. That is equal and opposite input signal voltages are not required to amplify the signals. That means this circuit can amplify the input signal voltages with varying positive and negative voltage peaks. That is the advantage. What is the drawback of complementary symmetry? It is difficult to get a pair of transistors which have similar characteristics. That means both these transistors should have a similar characteristics. Means what? Both of them should have a same cut-in voltage. That's the problem. Next problem is what? We require both positive and negative supply voltages. Plus VCC and minus VCC are the major things which we are going to have it over here. Okay. That means in order to overcome the problem which is there in the class B push-pull type of the power amplifier, we will be going with the class A type of the power amplifier. What is the major problem that the class B power amplifier is going to have? It is nothing but the crossover distortion. Class B push-pull power amplifiers are going to suffer a lot with the crossover distortions. So to avoid such crossover distortions, we normally go with the class B type of the power amplifiers. Okay. Now in general, what is crossover distortion? When the input is making excursions between high to low and low to high, that means at zero crossings, we are not going to have the signal. What is the reason being here? The reason is that the two transistors will turn into on condition only after the bias voltage, that is nothing but cut-in voltage, which is approximately equal to 0.7 volts. So only after 0.1 volt, the transistor will be simply turning into on condition. So because of this reason, the crossover distortion is normally going to take place. Say for example, when T1 transistor is turning into on, it turns on only after 0.7 voltage. That means that much voltage is simply going to get avoided here, or totally going to get cut off. Now after 0.7, the T1 transistor is going to allow the signal to flow through it. So after T1 turns into off condition, T2 turns into on condition. When the T2 will turn into on condition? Only after 0.7 volts. That means the T2 transistor will not turn into on condition up to 0.7 volts of the input signal. So therefore, that much portion is not going to get transmitted to the load resistances or load. That means this signal is simply going to come like a distorted signal. That means the overall waveform, if you see, the overall waveform is going to look like a distorted waveform with respect to the input waveform. The input waveform is going to be a perfect AC signal, but output waveform is going to come up like a crossover distorted waveform. So therefore, the output waveform is simply known as a distorted waveform that we are going to get, which is simply going to happen because the two transistors will not turn into on condition before its cut-in voltage. That means what is that? Why this particular problem is happening? Because the Q point is adjusted to a level such that only 180 degrees of the input signal is going to get transmitted. That means the Q point is adjusted on x-axis of the output characteristics. So because of that reason, we are getting the crossover distortions. So to avoid this, what has to be done? The Q point has to be adjusted. That means the Q point has to be shifted. It has to be shifted between 180 to 360 degrees. Therefore, the firing angle of the class AB power amplifier is going to be 180 degrees to 160 degrees. But the firing angle will be more close to 180 degrees than to the 360 degrees in order to provide the effective operation. Why? Because we have only 0.7 volts. So this up to this 0.7 volts, the transistor which is in the on condition has to be in the on condition until the other transistor turns into on condition. Then the crossover distortion is simply going to get avoided. Or otherwise, what you can do is something like you can clamp the input voltages of T1 and T2 transistors to a level of 0.7 volts. That means if you apply some bias voltage to Q1 and Q2 transistors such that such that by the time when zero crossing takes place, the other transistor will turn into on condition. That means two transistors can be in the on condition at a time to avoid the crossover distortion. After some little amount of time period, then the switchover takes place totally. That is one transistor turning into on condition totally, other transistor turning into off condition totally. So that condition is normally achieved after this particular thing over here. Okay. So here in this particular characteristic graph, we are showing the basic problem that we are really facing in the class B type of the power amplifier. See the input signal. Input signal is simply making excursions on the average DC line. And if you are seeing this particular waveform is a smooth sine waveform. When it comes to the output side, see here, there is no signal in this zero crossings. So therefore it is known as a crossover distortion. That means the distortion of the output waveform at zero crossings is simply known as the crossover distortion. So what is the reasons of going for crossover distortion? Cut in voltage. So since the transistor will not turn into on condition, before 0.7 volts, we simply call it as a crossover distortion. So now this zone is simply called as a dead zone. Dead zone means what? No output signal is going to come. Therefore, it is known as a dead zone, right? So, and in order to overcome this, what we have to do now? That means as the input voltage is increasing from zero, output should also increase from zero. Okay, that is what we are supposed to get. To get that, what has to be done now? Every transistor has to be pre-biased to 0.7 volts, right? So when we could able to achieve that, if we could able to achieve that, then definitely we normally going to avoid the crossover distortion. Now that can be done only when we shift the Q point above the zero level. That means we have to shift the Q point above 180 degrees phase shift. So to do that, we simply going to do that in a class AB type of the power amplifiers. That means after we do that, after we shift that Q point above 180 degrees phase shift and below 360 degrees of the input signal firing angle, we call that type of a transistor as a class AB type of the power amplifier circuit. Now, as I said, it will be confusing. Class AB power amplifier, class AB power amplifier, class AB complementary symmetry power amplifier is all confusing because everywhere we are going to use two transistors. All the three cases in class D also we use the two transistors. So that is why it will be somewhat, you know, little bit you know, confusing kind of thing over there. Okay. So we have to clamp the input voltage to 0.7 volts by using some biasing networks. That means here instead of D1 and D2, you can have simply something like, I can take this as R1, I can take this as R3, I can take instead of D1, D2, I can take R2 also. I can just name these resistors as R1 and the resistors between bases of T1 and T2 can be called as R2, and I can have one more resistor here going to be called as R3. So as it is a PNP transistor, it should be negatively biased with minus VCC, and here it is going to get NPN transistor reverse biased with plus VCC. PNP transistor is reverse biased with in the output circuit. It is reverse biased in the output circuit with minus VCC, and NPN transistor is normally going to get reverse biased in the output circuit by plus VCC, which we already know that. So apart from that, if you put just a resistor here, this resistor is going to clamp the input voltages of T1 and T2 to 0.7 volts. That means if the input voltage is going to be you know, negative side or positive side is going to be more than 0.7, then only the true action of the two transistors are normally going to start into effect. That means the effect of two transistors turning on will take into effect only due to the cause of the input voltage which is greater than the cut-in voltage of the two transistors. So that is how we normally going to achieve this particular condition. So crossover distortion happens only in the transition period. That means transition means what? Q1 turning into off condition and Q2 turning into on condition, or vice versa. That means Q2, T2 turning into off condition and T1 turning into on condition. So there only the crossover distortion is going to take place. So to avoid that, what is that we are simply doing here? I'm just putting two diodes here, D1 and D2. So these D1 and D2 are going to clamp the base voltages to 0.1 volts. If you consider the cut-in voltage of D1 and D2 are equal to the cut-in voltages of T1 and T2 transistors. That means the base emitter voltage of T1 and T2, if it is equal to the cut-in voltage of D1 and D2, then only we can able to achieve this particular task of eliminating the crossover distortion. Okay, so if we assume that the characteristics of PN junction diode and the input characteristics of two transistors are going to be same, then we can simply eliminate the crossover distortion. Now, if you could not get such a diodes, then we can use a resistor. Now, getting different types of resistors is very easy task. Why? Because you can get different values of a resistor by using a potentiometer also. Therefore, we can easily achieve by using a resistor. That is what, this is one example of construction. You can draw the same diagram by simply drawing a resistor instead of the two diodes over here. Okay, so anyway, that is how the circuit diagram, which we can just see another circuit diagram in the next day's class, tomorrow's session. I go with another variety of the circuit of class AB type of the power amplifier. But currently I am going with the one version of the transistor circuit of class AB. Now what happens before we apply the input signal? What is the condition of the two diodes T1 and T2? Let us try to observe the case. That the condition of diode is what now? Diode D1 is positive biased here. Diode D2 negative terminal of the N type of the diode is connected to the minus VCC. That means it is more forward biased. What about this? This is zero potential. That means you are applying more positive voltage to the diode D1 and D2. Therefore, D1 and D2 will be in the on condition. When D1 and D2 are in the on condition, what is the potential that D1 and D2 can be replaced with? I can replace D1 and D2 with a battery of here positive 0.7 volts. Here I can replace this with a negative 0.7 volts. That means initially what is happening? The transistor T1 and T2 are in the on condition, right? That means you can apply starting pulse as a negative pulse or a positive pulse, doesn't matter. The circuit starts operating, right? By eliminating the crossover distortion. All right. So if, for example, the input voltage is taking a positive peak, D1 and D2 both are in the on condition. All right. So because of this condition, what is going to happen now? The transistor T1 will turn into on condition because positive portion, this is NPN transistor. For NPN transistor, if you apply a positive voltage, it will be turning into more into on condition. So it is going to transmit this particular signal, right? And that is simply calculated the output, right? So in the transition period, what is happening? That is what the point we have to really discuss. In the transition point, input is zero. When input is zero, transistor Q1 still is in the on condition. When the input is taking negative, what is that which is happening now? Transistor T2 will simply turn into on condition. It's already in the on condition. It is going to allow this negative spikes to go into the transistor, whereas this negative signal, this transistor T1 will be in the off condition. That means that the voltage across diode is simply taken as a clamping voltage. This voltage is normally going to work like a reference voltage or a threshold voltage, which is of range of 0.7 volts. Okay. So with that, we normally going to achieve this particular condition. Okay. All right. So that means if a temperature changes, VBE changes, accordingly, the voltage across diode should also change. Thereby it provides some little bit of temperature compensation also for us. Okay, so with this we can say that this particular circuit is normally used to transmit the complete cycle of the input signal without any distortions at zero crossings. So that is what the benefit that we are supposed to get over here. Okay, then after this, now that means what is the response curve that we can just observe here. So the Q point was on the zero line, on the zero axis, when it is acting like a class B push-pull type of the power amplifier. Now the Q point is simply shifted to a portion just above the zero level to a value of 0.7 volts. If it is adjusted to a level of 0.7 volts, then what happens? The signal is simply going to get transmitted in this gray portion. This gray portion is nothing but the signal transmission portion. The signal is simply getting transmitted in this region for a particular transistor. That means a particular transistor will be in the on condition even in the region below the average DC. This is normally going to avoid the crossover distortions. So this is how we normally avoid the crossover distortion, by using the class AB type of the power amplifier circuit. Okay, so in the next section we'll see one more version of the class AB type of the circuit, and we'll try to discuss about the class D power amplifier circuit. So with that we'll end up this particular unit as far as theory is concerned, and after we complete this theory in the next session we'll try to do some problems on the power amplifiers. Okay, so till then, thank you very much for today's session. Okay, we'll stop our session here.